and the light will turn on.
Okay.
And that means your mic. This is Salt Lake. Are you guys talking yet? We can't hear you.
Yeah, it's 20 minutes, 20 to 25 minutes. Yeah. Started? Oh, we can start it, right? It's ready, right? Okay.
Okay, let's get started. Doug is actually in DC with Rob at the water quality meetings, I believe. So they're actually watching streaming, and Dylan, do you want to start with just introducing yourself and a little bit about what you do, and then
Yeah. My name is Jimmy Jin. I'm from Watershed Sciences and also affiliated with Department of Plant Soils and Climate Department. So yeah, today I just talk about, since I just have 20 minutes, so I just talk about some previous results we have done. But next Tuesday, I'm gonna give a department seminar. So that in that seminar, I'm gonna focus on the regional climate modeling. So it's 4 o'clock, Federal 4 o'clock. Which room? It's being 102, yeah, 102. That's going to be an hour seminar, right? So I wish you guys can attend. So that's my recent results. I will present some of my most recent results in that seminar. So today I'm going to talk a little bit about modeling and analysis of snowpack over the western United States. So you look at this map. This is snow duration trend. Duration trend global snow duration trend observed value. This value is based on satellite data. So this is Western United States here. So that's the warm color here. That means duration is shortened. It's shortened, compared with previous period. So you see, the Western United States, the snow duration is shorter than before. So also Alaska. This is Alaska. In the southwest part, Arizona, New Mexico, you see snow duration is longer than before. That's going to be intensified. That's caused by intensified precipitation there. From observed value, we see the precipitation in that area is increases instead of decreases in recent year. This is a close look of snow depth trends over the western United States. Here, the dark dots here, it's positive trends, upward trends. The gray dots here, it's negative trends, that's downward trends. The open circle here, that means the snow change, it's not significant, So you see most decreased trends is decreased trends are over the northwest. The southwest either doesn't have significant trends or have upward trends here. You see the dark dots here. This picture shows Mount Hood, so in Oregon. You see, this picture was taken in 1985. You see, this is snow during that year. But now this is took in which year? It's 2002.
Those the same time of year?
Yeah, that's I'm wondering. So that I believe I can trust this photographer. It's called Gary. So I believe it's the same year. This is published results. I think should be trusted. Should be trusted. So this is another figure shows snowfall and rainfall. In 1968, this blue color that represents rainfall. This light blue color is mixing of snowfall and rainfall, and the white color represents the snowfall. You see, in this year, during 1968, mostly the snowfall is quite dominant, or snow rain mixed pattern is quite dominant. But in recent year, the rainfall is very dominant. This location is in watershed in Idaho. So that means something give us a hint of global climate change affect the local snow pattern. This is a model of projected results. This is current situation. This is still snowfall. So based on a lot of model, it's composite results of a lot of model from a lot of models. So this is California, this is Oregon. You see, this is current situation for the snowfall. By 2050, you see snowfall is significantly reduced by this kind. So this is also related to global warming, something related to global warming. This is snowpack over the mountains. Over the mountains, this is New Zealand, Western United States here. This is current situation. The top is current situation. This is Himalayas, so this is northern USA. So the bottom pattern is for the end of a century. So by end of a century, you see the snow in the Western United States, snow reduced to the 57% when comparing the current level, compared to the current level. Yeah, I think this is good news because some model prediction is by end of a century there is no snow in the Western United States, so it's more, but this still have like half of snow in this area. So yeah, it seems like the global climate have a very significant impact on the snowpack in the Western United States. How another process affect snowpack in the Western US is interannual variability of atmosphere. So there are two factors affecting interannual variability of snow. One is called internal variability of atmosphere. Another one is ENSO. The internal variability of atmosphere usually represented by PN pattern. That's called the Pacific North American pattern. This pattern, so we use this geopotential height to calculate the PNA index. So based on this geopotential height, Z here represents geopotential height. This is location. Based on different location, we can calculate the PNA index. So for the spatial pattern, so see this is called, when the PNA pattern, PN index is positive, they call the positive PNA pattern. When this value is negative, they call the negative PN pattern. You see, this is positive PN pattern. You see a high pressure over the almost entire United States, mostly focused on the Western United States. The low pressure is along the coast of Canada, so west coast of Canada. So over the Aleutian Island, there is high pressure here. This is, if we have positive PN pattern, we have negative PN pattern. This is how negative PN pattern looks like. This pattern is totally caused by internal atmosphere, nonlinear process of atmosphere. It's no out-of-forcing for this pattern. So that means this is one pattern affect snow spatial distribution and snow depths of in the Western United States. Another process is ENSO. That's a trigger from sea surface temperature anomaly over the tropical Pacific. So ENSO, we have two kinds of ENSOs. One is warm ENSO, that's also called El Nino. One is cold ENSO, that's called La Nina. So that means over the tropical, during the warm ENSO period, over the tropical Pacific, the sea surface temperature is above the normal. But during the cold ENSO period, so the tropical Pacific sea surface temperature is below the normal. So during the warm ENSO, you see this is snow anomaly. That anomaly means the difference from a long-term average value. Here, dark dots here is positive anomaly, and the gray dot here is negative anomalies. The open circle here is, that means snow doesn't have significant changes. So during the El Nino, that also warm ENSO, you see southwest have a significant increase of snowpack, but northwest you have slight decrease of snowpack. During La Nina period, so northwest have a significant increase of snowpack. So you see these dark dots represent positive anomalies. But southwest have slight decrease, snow have slight decreases. But under the positive PA pattern, that atmospheric pattern, so entire western United States snow is decreases. But during the negative PA pattern, almost the entire western United States snowpack decreases. So this is full pattern that causes snow interannual variability of snow. So what process causes these snow anomalies? So we applied UF functions, UF to these snow depths. So the UF is called empirical orthogonal function. So that's basically retrieve dominant snow variability pattern. So there's no, this is, this is, can you see it? Can I go put down this screen a little bit?
We can't see the very top one.
Yeah.
With the projector,
I have no idea. Yeah. How to control this? There cannot stop. This is like so. Yeah, okay, this is good. Sorry about this. So we apply this function to the snow depths, snow depths here. So we retrieve a spatial pattern based on US application. So this is first the most dominant pattern of UF. You see this pattern is a mimic of a snow anomaly on the PA patterns, right? Over the entire United States, snow changes. But this pattern, second UF pattern, you see, this pattern mimic of ENSO pattern. So the difference between northwest, the snow are different between northwest and the southwest. So that means the first pattern account for 39%, almost 40% of variance of snow variability. But the second pattern is account for almost 20% of snow variance. If I put it another way, that means if you want to predict snow, if you only based on PA pattern, so your predictability is 40%. But if you want to predict snow for the Western United States, you only based on ENSO. That's your predictability is 20%. So that means that's another interpretation of these two figures. Now we need to understand what caused the snow anomalies. So first we look at the precipitation patterns. This is a precipitation anomaly for the warm ENSO in the Western United States. This dashed line here, that's negative anomaly. And a solid contours here is positive anomaly. This dotted area, that means the changes over that area is very significant. It's past the 95% of a significant level. So you see, during the warm ENSO, the southwest have a dramatic positive precipitation anomaly. That causes higher snowpack in that region. But northwest doesn't have a very dramatic change, but still, so the precipitation decreases in that region. During the cold ENSO, you see the northwest have dramatic increase of precipitation, but the southwest doesn't have that, precipitation doesn't have as much changes as for the northwest. So another thing, you look at temperature, so snow affected by two variables. One is precipitation, another is temperature. So for temperature, you see during the warm insole, so northwest you have over the northwest temperature increases and southwest temperature decreases. The cold temperature here also help produce high snowpack in the southwest. But for the during the cold insole period, you see almost the entire western United States have negative bias, not bias, negative anomalies. From this pattern, these two patterns are not consistent. That means temperature is not directly related to snowpack. So based on these figures, we can clearly see the precipitation have a very dominant impact on the snow anomalies during the insole period. So this is the atmospheric circulation pattern, anomalous pattern during the insole period. So the top one is for the warm insole, the bottom one is for the cold insole. This is for 500 geopotential height anomalies. Still, dashed line here is negative anomalies. Solid contours here is positive anomalies. During the warm insole, you see this is low pressure here. Low pressure here, almost low pressure, it covered a large place of the southwest. This low pressure caused the stronger precipitation in the southwest. But for this pattern, you see the most over the northwest, its low pressure is quite dominant. This also low pressure caused the stronger precipitation in that region. So this thick dashed line is a ridge, climatological ridge. That means if you do the long-term average, you always find a ridge there, atmospheric ridge there. So if you have a ridge, you have good sky. You have clear sky and good weather. You have a trough, you have a bad weather, raining atmosphere, rainy weather. So you see during the warm insole, this south part of this ridge is weakened. That means, so that causes no pressure here. That brings a lot of moisture from Pacific to the southwest. But during the cold insole, you see the northern part of this ridge is weakened. So this also brings the moisture to the north with increased precipitation in that region. So this is the geopotential height anomalies for western United States. So this is precipitation and temperature anomalies of the western United States on the PNA pattern. So you see these two patterns, the precipitation anomalies. This is for positive PNA pattern. This is on the negative pattern. This is based on these two patterns. Precipitation doesn't have a systematic pattern, right? So this significant change is quite spotty. But you look at temperature. Temperature is very strong anomalies here. It's very significant. This is for the positive PNA pattern. Temperature is increases. Over the negative PNA pattern, temperature decreases. This increased temperature result in the lower snowpack. The decreased temperature result in the higher snowpack. That means that under the PNA pattern, temperature has dominant impact on snow anomalies. This is different from insole. Insole, precipitation have very dominant impact on snow anomalies. So this is how the PNA pattern looks like in the 500 geopotential height anomalies. So during the positive PNA pattern, you see there is a positive high pressure here. High pressure is very dominant over the entire western United States. This is caused high temperature because you have high pressure, you have good weather, you have clear sky, you have a high temperature here. So during the negative PNA pattern, you see the low pressure is very dominant over the western United States. This causes low temperature here. So that means the low temperature is caused by atmospheric circulation. Again, the PNA pattern, there is no forcing. There is no triggers. That's totally caused by nonlinear process of atmosphere. So yeah, snow, so after we see, how atmosphere climate affect the snowpack over the western United States. Now we try to use our model to simulate this snowpack. First we will check if our model is able to simulate this snowpack. This is the snowtail stations. Over this station, this is automatic station. They measure, so these stations measure snowpack, temperature, and precipitation. This is over the Sierra Nevada region in California and Nevada here. So there are 26 stations in that region. So first we use our regional climate model. This is called 5th generation mesoscale model. This is NOAA landscape model, so snow component is in this landscape model. First, we apply our model to that region. So this is a time series of snow depths. This solid line is observed value averaged over those 26 snowtail stations. This is simulated, so model simulated. See, the model did a very poor job, significantly underestimated snow depths. So now, for meteorologists, they see a process or a variable can significantly affect the atmospheric process. They will pay attention to it. Otherwise, even like stream flow, most meteorologists, they don't pay much attention because stream flow doesn't have a strong impact on the atmospheric processes. For snow, it's the same thing. When we look at these patterns, we replace this observed value in the model with this simulated value to improve. See how snow affect atmospheric processes. So in this figure, this time series of 2 meter high air temperature. This solid line here is observed value. This dashed line here is original model simulation, also averaged over those 26 snowtail stations. So this dotted line here, if we replace simulated snow with snow observation, we produce this dotted line. You see, if we are unable to simulate good snow, the temperature have dramatic changes. For the, for the original snow, for the temperature bias is 4.7 degree. So after we replace the simulated snow with observations, bias reduced to 1.3 Celsius degree. So that's dramatic reduction, bias reduction. So then we look at temperature here. This figure is a little bit busy here. So still, solid line here is observation, averaged over those 26 snowtail stations. The dashed line here is original model simulation without doing anything. But the dotted line here is if we replace the observed snow with simulated snow with observations, so we produce dotted line. Here, you see, original modeled bias is 53 millimeters. After we put snow observation in the model, the simulations, the bias became 9 millimeters. That's also a significant reduction of the bias. So what process caused this precipitation reduction? We see, so in precipitation in the model, there's two types of precipitation. One is called large-scale precipitation. That's caused by atmospheric circulation. Another precipitation is caused by local convections. So this is the first large-scale precipitation. So the total large-scale precipitation for the control run, that's original model simulation, is 218 millimeters. But after we put the correct snow in the model, the bias, the changes, the total precipitation decreases. But this is local convective precipitation. Convective precipitation, original model simulation is 55 millimeters. After we put the observed value in the model, it became 26. That means, so convective, from this four figures, you see convective precipitation have more dramatic changes. That means if you put the correct snow in the model, that will reduce atmospheric convections. So reduce that, suppress those convections. Because the original model have too strong convections. After we put the correct snow in, we reduce that convections. So that means this is how it changes. So after a while, you see snow is important, has significant impact on the precipitation and temperature. That's why we need to improve snow simulation. So how we improve? We look at the original. This is a new generation model. This model is called Weather Research Forecasting Model. This model is still based on previous generation, but have some improvement. So we use the new model to simulate the snow. This is over the Columbia River Basin. We showed NOAA simulation original. This is the red line is NOAA simulation. This dotted line, this is stars observation. So over the Columbia River Basin in the state of Washington, you see still have a dramatic underestimation of a snowpack, even with new model. So we are very disappointed with this simulation. This is another land surface model simulate the snowpack. Within that model, still have a significant bias here. So that was we think this model doesn't work. This is a bad model. So we coupled a new land surface model, new snow model into this WRF model. This model called the Community Land Model version 3, so Community Land Model. So after we couple this new model into this regional climate model, we see we have pretty much, realistically simulated the snowpack. Snowpack. So I will talk a little more about how we did this kind of simulation. What's some processes within this model next week in the department seminar. So this is pretty much we have done. So I give a little bit of summary. So over the Western United States, the two processes affect the snowpack distribution. One is global warming, global climate change. Another one is interannual variability of the atmosphere. This is both processes are very significantly affect the snowpack. So now, in order to more realistically predict the snowpack, so we improve a regional climate model to produce better snow simulations. So we can use this model to predict the future snow amount. Apply this model to the predictive future changes of snow mass. This is pretty much for my today's presentation. If you have any questions.
Maybe 5-10 minutes or something, since we've got a little time, and if anybody's got specific questions, and then we can switch over to our next presenter.
I know just enough to be really dangerous on this stuff. And so if I were to say what I dangerously know, or what I dangerously think I understand, it's that this part of the world right here, northern Utah, has a poor correlation in terms of how we respond to El Nino or La Nina conditions. I guess that's my first question. Is that true?
Yes.
Or am I wrong?
Yes, that's pretty much true.
That's true. Okay, so in the business of predicting what the future will be as affected by climate change, does the fact that northern Utah has a poor correlation with ENSO phenomenon, does that make the job of predicting the effects of climate change easier or harder?
In general, this is two separate processes, So first I answer your first question. First question, you see the Utah. Oh. Yeah. You see the Utah here. located the transition period, so especially northern Utah, transition period between the El Nino effect area and La Nina effect area. So the northwestern, transition period, the transition region of between northwest and southwest. So that means it's really hard, so use based on the ENSO to predict snowpack in northern Utah. So Simon once, he did a study. Actually, this I talk about the interannual variability. In the longer time scale, like decadal scale, so we still can use sea surface temperature to predict the snowpack. As a detailed scale, Utah snowpack have very good correlation with sea surface temperature. But at the interannual variability, this time at the interannual time scale, so that doesn't have a good correlation. So I think that's two separate processes. So you said, so it doesn't impact from ENSO. That makes our job easier or difficult, more difficult. Actually, it's not related, so it's...
Well, so when you say not related, the way I interpret that is it doesn't matter. The job of predicting decadal scale impacts of climate change is unaffected by whether you're in an area of the West where there's a strong correlation with ENSO or a poor correlation. The job of predicting the future is just as hard everywhere.
Yeah, because you have used because Simon one used a statistical filter to just focus on certain skills. They will filter out the other skills impact. That's why so I don't think it's if you can have a method to separate this impact, really doesn't matter. Just retrieve. The model has good, so for the model, you do sensitivity study, you just focus on one impact, right? Keep other impact the same, and focus on one impact. That's from my idea, it's really doesn't matter. It's maybe it's more difficult. I didn't try, so. But what do you think?
Well, I have no idea.
Yeah, I know. Yeah, because from my personal experience, it shouldn't be a big problem.
Okay.
Yeah. So,
Jermaine, you talked about a lot of the different factors which influence the interannual variability. How well in advance can we know or predict those factors?
Yeah, usually the normally 3 months in December, and so you will see the change in precipitation in March. Always 3 months ahead of time. But the is totally you have no control. Not in a process. Annual variability of the atmosphere. Parameter study for daily weathers you can because linear for daily weather predictions linear process is not that strong. After 7 days.
So you understand what's causing these effects, but you can't predict when those.
No, even PNF pattern we don't know reason. It's totally internal variability. For the ENSO pattern, you have sea surface temperature changes, so you have atmospheric circulation changes. Then you will see precipitation changes or temperature changes. So that's a process. But for the internal variability of atmosphere, you have no control. So they just randomly changes. But this we based on long-term average pattern. We see some pattern. If you based on for example, 1,000 year, you don't see that pattern will filled out. So because it's a quite random process.
Right.
Yeah. So
I got here a little late.
yeah.
But generally, is precip going to stay constant? Just less of it will be snow.
No, precipitation became more violent. Changes became more violent. Some dry place getting drier, wet place getting wetter. So that's some very dramatic changes. For example, people always think global warming causes Southwest getting dry. Actually, based on model predictions, they said, oh, Southwest is going to have a drought, so more severe drought in the future. But based on observation, actually precipitation increases.
Well, given the fact that the West is mountain islands, which have lots of precipitation, and intervening valleys that are dry,
Yeah.
does that mean that the islands of the mountain islands where there's lots of precipitation are going to increase in precipitation, while the intervening valleys are drier? Or is that too small a spatial scale for?
Yeah, too small.
Too small.
Yeah, too small. That so for the.
So what I said is wrong.
Yeah.
Okay.
No. Maybe it's correct, but
Well,
too
we don't
small
know.
to make
Okay, all right.
It is being empirical.
Yeah. So.
Yeah, no, I mean that.
Yeah, because this is global climate change. So scale usually large. You just based on one small watershed to make judgment. It's not reasonable. So you have to look at the larger scale pattern. So yeah. That's other questions. Yeah.
I wonder if the snowpack could be influenced also by other climatic parameters or maybe energy fluxes. What do you think?
Yeah, because snowpack today I two process. One is long-term climate trend. Another one is interannual variability. Also, snowpack impacted by seasonal changes. A lot of scales like decadal variability, seasonal changes, right? Seasonal changes sometimes the sublimation process also affect the snowpack. Even snow surface sublimation, because you get a very high snowpack during the spring, you don't see much runoff, right? That's because of the sublimation process. That's a seasonal process, but also decadal process. So today I talked about just two scales. One is interannual variability, because this is research I have done. But maybe you can look at different other scales. So Simon Wang did some precipitation changes with decadal. He's always focused on decadal variability of precipitation in the West.
Oh.
Yeah. Okay, so yeah.
Great. Well, let's switch to presentation number 2 here, and at the end we can see if we can pull these 2 things together as well.
Stand up, turn around, get your hands going.
Right. Pass the M&Ms.
Yeah.
There's some there's not there. They're going to be sitting if you want to go.
So we should remind people that Jeff's talk next Monday. Right, Dr. Torben?
Yes.
Okay, who would you like some old on?
So has everybody changed gears now? Everybody awake? Lucky I opened this presentation rather than the unit hydrograph one I just gave to my hydrology class. So 10:30 in Geology 105 next Monday. Be there, be square. Jeff McDonald is giving the Birdsall lecture on where does the water go when it rains. The Birdsall lecture is a Geological Society of America invited distinguished lecture. For those of you who have been at Utah State a really long time, which is possibly only me in the room, he used to be on the faculty here. Were you here when he was there? Jack was here.
1 year.
So he was here 20 years ago before he went on to greater things, and we're delighted that he's going to come back. So I would encourage everybody to go to that. Geology, room 105. And relevant to this group, he is one of the principal investigators of one of the funded water sustainability climate category 2 projects that deals with the Willamette River in Oregon. So he's at Oregon State University. So we should try and pick his brain as much as possible about how he managed to pull it off. So what I'm going to talk about is hydrologic modeling to quantify watershed functioning and predict the sensitivity to change. I didn't want to just make this a talk about my research. I rather sort of grappled with what I thought might be most appropriate for helping us get towards the water sustainability and climate project. So you'll see my ideas. It might be a little bit different than what I had before. So in terms of outline, I'm going to give a bit of philosophy, talk about the sort of question-driven approach and the appropriate simplification for modeling. I'll go through one of the examples that comes from my research, and then I'll talk about a framework for thinking about water balance and change, and then offer a few thoughts at the end. Before getting into the philosophy, just a bit about my research and its focus. I like to try and describe my work as advancing the capability for hydrologic prediction by developing models that take advantage of new information and process understanding enabled by new technology. It's a mouthful of a sentence, but I think it sort of tries to capture in one sentence a lot of what I do, which is depicted in some of these pictures at the back in terms of looking at landslides coming off roads, looking at stream flow from small watersheds, looking at snow and snow melt. Those little mountains in the background there are the Wellsvilles. That's one of the few times I've been up at the top of Logan Peak, and I need to get there much more often. Tomorrow? You're going there tomorrow? Thursday next week. Okay. So some of the areas I've worked on that fit into this is hydrologic information systems, which is more about the information science than sort of hydrologic science, but it involves the taking advantage of new information, terrain analysis using digital elevation models to delineate watersheds from DEMs, looking at climate change impacts on hydrology and stream ecology with jimming, and then snowmelt modeling, as well as looking at impacts of land cover change on stream flow. I guess that's work with Ibrahim, who graduate student of mine, some work on the Great Salt Lake, and then trends in stream flow, which is work with Margaret. But in terms of philosophy, I wanted to emphasize this at the beginning because in terms of getting things successfully funded at the National Science Foundation, I think this is critical. This is from an invited commentary by Jim Kirshner, who was one of the principal investigators on the Central Sierra Critical Zone Observatory that was funded. So he's also got some credibility to speak to what's important. He's a well-known geomorphologist who works in the hydrology area as well. And he wrote in this invited commentary, "The questions that we ask as scientists shape everything that follows." It's one of my favorite quotes. They can lead us to see the world in new ways or mundane ones. They can spur the development of new approaches or the recycling of established ones. They can focus our attention in useful directions or leave us wandering aimlessly. So there's one thing I've learned in my going around with the work in Quasi and the Waters Network is that people spend a lot of time trying to frame the question in a way that's going to actually direct the investigation in a fruitful way. So I would recommend reading this invited commentary. It's only 4 pages. It gets into some of the paradoxes in catchment hydrology and geochemistry, but also the philosophy it gives is wonderful. So in terms of one of the questions, this is the question that the now continued Waters Network framed. How can we protect ecosystems and better manage and predict water availability and quality for future generations. So that's a sort of a real broad, sweeping, overarching question. Perhaps it was too broad, and that perhaps led to that program not getting the success and focus that it might have, except that the Waters Network science plan was significantly relied upon in writing the Water Sustainability and Climate Call for Proposals, which we responded to. So there's a significant history there. This shows how when we were working on that report, we took that grand question in terms of protecting ecosystems to better manage and predict water availability and distilled it down into specific questions under each of the groups: hydrologic science, engineering, and social science. So you can see the sort of integration of the perhaps, well, the natural environment, the built environment, and what people do in terms of what would be investigated. How is freshwater availability changing, and how can we understand and predict these? So most of my research would probably fit into that area. How can we engineer water infrastructure to be reliable, resilient, and sustainable? A lot of the work of us in the Water Lab and engineering will be working on that. And then how will human behavior, policy design, and institutional decisions affect and be affected by the changes? I'll go through an example later today that gets into some of how human behavior is altering the hydrologic cycle and how we might model that. So then with the Waters Network, we're looking at the observations and resources that would be needed to answer those questions. So then, some more philosophy. This is a book by Peter Eagleson, who was one of my mentors when I was at graduate school at MIT. It's ecohydrology, Darwinian expression of vegetation, form, and function. I just want to read some things that I really like from the preface. I wouldn't dare to get into the details of the mathematics because he has a whole book on sort of optimal form function type stuff that would be, well, I think it'd be good reading if you're really into this sort of thing, because it's pretty deep theoretical ideas. He starts right at the beginning with what I've got at he starts with a question. I explore and evaluate the biophysical relationships between ambient climate and the form and function of the associated vegetation. I hope the results will be useful in anticipating the changes to be expected in vegetated surfaces under conditions of slowly changing climate. So he's sort of, and I only put part of it there, he's summarized where the book is going. He wants to understand form and function and its relation to climate change. Then later on he talks about the land surface atmosphere boundary conditions being interactive, the sort of things that Jimming was talking about in terms of how the snow related to the temperatures and the precipitation. Well, here the context is the vegetation. What vegetation grows there controls what water vapor gets pumped up into the atmosphere, how the energy balance works, and everything interacts. And then he says he's focusing on the theoretical generation of these atmospheric boundary conditions, which are necessarily highly idealized. So he's building a theory, an idealization to try and help understand things better. And he gives this quote from John Monteith. In a topic such as this, progress can be made only if the number of variables is held to a minimum at every stage of the analysis. So there's a focus on the sort of the necessary simplification. How do you build a model that captures what you need to, but is still tractable? So he then goes on and talks about many details being neglected, and then he starts appealing to his audience. And I've just put sort of XXXs and YYYs there, but he says, ecologists, micrometeorologists, and plant scientists will likely find this approach to be naive and may even be offended by my neglect of much important natural complexity. So then he says, Engineers, on the other hand, that's the Y by Y, will be familiar with and may welcome the reduction of an intricate interdisciplinary problem to a small set of simple, albeit approximate rules. In either case, I ask the reader to withhold judgment pending the presentation of evidence. So I guess he's setting up the purpose for it. And then at the end, he says, in multidisciplinary endeavors, all the rich scientific detail of each contributing field can't be retained in their joining, lest the resulting complexity negate the utility of the result. And I think that's exactly the problem that we're going to be grappling with in this project, because it's multidisciplinary. We're going to have to communicate and capture the information from all of the disciplines. We can't retain all of the complexity and still get anything done. So I thought that was, when I read this preface, I mean, I thought it was just said the things just right. So here's what perhaps is my main point of this presentation. We need to, in thinking about this project, strike a tractable balance in the representation of process complexity from the different disciplines. And that probably will have to involve building an integrated model and the associated data and information system to support that model. So if we think of building some sort of model, some sort of computer simulation model as part of this project or the greater project that we propose, I think the model has the following purposes. It's a way to encode and encapsulate knowledge. We represent our understanding of the way something behaves by how we represent it in the model. It then can be used to test hypotheses, because we then compare that behavior that we've encoded with the measurements to see if we get it right or didn't. It's a way to formalize the communication across disciplines. If we each can, it's a way to force you to actually be precise about what your understanding is of how the system works, or your part of the system, so that the other discipline can try and use it, and you can try and represent what your specific part of the model is in a specific way. But I also think it's a journey in research. The model is not the end point. It needs to involve a continuous dialogue and be continually evolving, continually investigating the why do the outputs look like this, and what does that mean. It's a process of discovery, because by putting things in the model and looking at how the results come out and intercompare, we will hopefully learn something. And it should involve frequent iteration and adaptation. So there's elements here that I've sort of adopted from presentations I've seen by people like Roger Grayson talk about adaptive environmental management, which is one of the buzzwords that's used sometimes in the environmental area. And I know Jack's been involved with some adaptive management efforts in the Colorado River. I think this has got elements of that, but it's not exactly that. But the frequent iteration part of it is something that I think is important. So this is my main message today, that I think we need to think about as we approach this project to try and bring it and bring something together. So I'm going to give an example, digging back into my past work, of distributed catchment scale water resource planning model that was developed here at Utah State, that had some of the elements of what I'm talking about, not all of them. This was a large study that several of us were involved in what we knew as the Nooksack watershed, water resource inventory area, one in northwest Washington County, well, in Whatcom County in northwest Washington State. And we put together a hydrologic model for decision support that had each of these drainages as model elements and examined the sort of spatial patterns and changes due to development and water resources management in this area. And there were some really good things that went to this, and there were also some real big challenges. One of the big challenges was that I think we didn't iterate enough. We only sort of put the thing together right at the end and shoved it out the door, and it didn't serve the purpose of actually bringing everybody together to communicate. So this is the sort of flow diagram of that. And some of the issues that this model was designed to address were competition for water resources among users. When I first started this project, I was really surprised. I mean, this is northern Washington State, one of the wettest places in the country. Yet they're squabbling over water. And here we have a team from Utah, one of the driest places in the country, to go in and try and help them out. So there was a lot of irony there. But there was competition for water resources among users. Human activities can alter the water balance, having effects on stream ecosystems and water quality. So this part of the model is only the hydrology part that I was involved with. It was connected to a water quality part that David Stevens was involved with, connected with a fish part that Tom Hardy was involved with. Jeff, you were involved in the water quality part, were you? And also the decision support system, which sort of put the whole thing together. And then simulation modeling is used to quantify the likely impacts of water management choices. So what we've got here are things like the simulation of the climate. The precipitation input needs to get separated between rain and snow, and then the snow melt needs to be simulated. Then this is the sort of more natural runoff, rainfall runoff transformation part of the model, where you have canopy interception, soil moisture, deeper groundwater, then channel flow. We've got some artificial aspects. There was artificial drainage. So I know there was one of the talks earlier spoke about tile drains and how to represent tile drains. Well, we took a stab at putting tile drains into this model as one of the human alterations. Then there's the whole business of water management, withdrawals that can come from surface water or groundwater. Then they go to irrigation, which acts as though it's sprinklers, which falls on top of the canopy, or drip, which falls beneath the canopy. So the sprinkler irrigation was sort of subject to interception, whereas the drip irrigation was not. Non-irrigation water uses, and then non-irrigation return flows to groundwater and surface water. So we tried to represent many of those things. And then we also had, obviously, the evapotranspiration part of it, potential evapotranspiration driving evaporation from the soil and from the canopy, effectively driven by weather input. So it was an effort to put together a lot of what was there. So I've just got a number of slides that go through some of the model components. I'm not going to dwell on all the details, because it's really not the details of the model that's important, but it's the sort of the style of using a model to encode the knowledge, to really communicate about processes and consequences and change and sensitivity to change and things like that. But it was based on Bevan and Kirkby's top model with additional parts for kinematic wave routing of water through channels, interception, a soil zone that keeps track of soil moisture, and a GIS parameterization that allowed you to quantify the spatial inputs from geographic information. So we did work on things like maps of the soils to come up with soil parameters, and there were a whole bunch of database table lookup type of work that was involved in setting that up. Vegetation parameters, so there's things like the canopy interception capacity, the albedo of vegetation, and we looked at historic pre-settlement estimates of what the land cover was. Nobody was here to see it, at least nobody that could record an aerial photograph. And then existing conditions where you've got much more agricultural and urban and residential development. So what is the changes due to that? And those come into the model through these models, and have we got the sensitivity of it right? Well, the model simulates what the change is, but validating it is quite a challenge. We've got things like the distributed energy balance snowmelt model that I've developed over the years, because it's a very much a snowmelt driven process, or a lot of it's the uplands are snow processes. And this is actually not a picture from that area. This is a picture from Reynolds Creek that just shows the spatial variability of snow and the importance, therefore, of accounting for the fact that you have a snow-covered area fraction and should represent that somewhere in the snowmelt models. Artificial drainage. So we had maps of things like this is where it's ditch drained and this is where it's tile drained. So we tried to add into the model capability to take water away, given ways that the users could specify what the drainage rate is from those areas when it's subject to ditch and tile drains. We try to build in a lot of the water management. So we talked about sources of water being either a reservoir, a stream, or groundwater, and the withdrawal was limited by availability and water right. So we had tables where each water source had a water right associated with it, and the model would look and see, oh, there's a demand on water from this source. Have I exceeded my water right? No, I can take the water. Is there water there? If there's no water there, then you can't take the water, and it sort of goes on. If there wasn't water there, well, if there was water there, then it would take the water. Then the uses were irrigation. So irrigation was driven by the soil moisture, the idea that the farmers are going to irrigate to keep the soil at field capacity. Then there were also non-irrigation water uses where a lot of those were effectively per capita driven, but the capita wasn't only people. I mean, there was a per capita of people in the cities, there was a per capita of cows and per capita of hens and per capita of all sorts of weird things. And we had a different per item water demands. And then as those changed, the uses changed and it all got simulated. So we're simulating agriculture and urban, and then also diversions. So I'm just going to go through now a series of slides that illustrate some of the issues that had to be dealt with in putting together a model like this. This is where precipitation is actually measured. So the green places are precipitation gauges. So we had a procedure where we sort of interpolated linearly between each precipitation station using fitting a surface of triangles, of Delaney triangles. So if we're dealing with a catchment in here, you may be estimating the precipitation from some places fairly far away. So just quantifying the inputs is a challenge and adds uncertainty to the model. Those are the locations where there were stream gauges that had sufficient records to try and either calibrate or validate the model. And well, the small triangles are that. We also found that well, we decided that the upland parts of the watershed were actually better just to use, for the purposes of what this model was being used for, to use the observed stream flow rather than try and simulate that, because all of the decisions that were being made were in the downstream areas. So let's at least help the model get the amount of water in the river right by sending observed inflows in rather than trying to simulate the upstream flows. So we had upstream boundary conditions that represented everything effectively to the right of those big green dots. So this shows some of the calibrations. We ended up looking at about, well, probably 20 or 30 stations, and we compared modeled flow versus measured flow, looking at the hydrographs. At the top here, you may not be able to read it. There are sort of error statistics of how much the model flow is of the measured flow. And we also looked at differences. You can see sometimes the differences were actually fairly significant. And also notice that the measured flows often have big gaps in them. The stream flow data just wasn't complete. So we were dealing with those sort of challenges and trying to sort of assimilate all of that information and getting the model to represent what's going on. So this illustrates the impact on stream flow of present land use. So we did a number of simulations effectively asking what if type questions. This particular one is a ratio of the simulated existing stream flow without water management to simulated historic stream flow. So the difference here is really the land cover changes that I showed in those two maps earlier, but no withdrawals, no irrigation, things like that. And you can see if the dark colors are where the flow has actually increased, and the lighter colors are where the flow has decreased. And initially it's a surprise to people that say, oh, well, there's more water there than we had historically, so why are you short of water? Well, what's happened is it used to be pretty swampy, pretty wet. You would have evaporation at potential evaporation rate. Now they've put all these tile drains in to drain the fields. They've paved over some of it to drain the water. And you're ending up, you've actually reduced the amount of evaporation, and that must increase the stream flow. So that doesn't say anything about the timing of it. We have detail about the timing of that as well. Then impact on the stream flow of the present water use and management. Now we're just looking at the difference between if we don't simulate the water uses and if we do simulate the water uses, where are the big differences? See, some of these rivers here are having a mean annual flow that's sort of, well, 50 to 80% of what it would have been without the withdrawals. So they're being significantly depleted. Some of them are increasing, and that's because there's actually a trans-basin diversion that takes water from one location and transfers it to another. So some of those flows are increased, and then where that gets taken out to go to the city of Bellingham, it decreases again. So you can examine sort of spatial patterns like this to see the impact of water management on the stream flow. We also looked at the hydrographs, and these are just illustrative hydrographs at some of the locations for if you don't have the model uses and you do, what's being simulated. So red is without water use, the blue is with water use, and you see the streams some of them are being simulated to be dry because the water demands are taking all of the water for certain parts of the year. And then you can look at the user withdrawals and see irrigation withdrawals fluctuate quite a lot because that's driven by the climate. Then you've got residential water uses, commercial, industrial, transportation, and dairy water uses that remain flat, except at places like that where the river goes dry, they don't have any water to take out. We also looked at scenarios of what happens when development continues, and there was a full build-out scenario representative of the future, sometime perhaps 15, 20 years ahead. And Lake Watcom, which right now is used as a storage reservoir but essentially remains full all the time, would have significant excursions below full as people start using it for what I guess the city of Bellingham and the water engineers intended use of that is as a water reservoir to supply water. Unfortunately, people have got used to the water being full, and they've developed their houses and their boats, and it's not dissimilar to Bear Lake, where people like the water to be up at your properties. Yet, if you're using it as reservoir, you expect it to be up and down, and that's the same with Lake Powell and Lake Mead. We simulated the discharge from Lake Watcom under the different conditions. We looked at water balance of specific areas. So this table shows essentially where the big water balance terms, what's happening to the water. Where does the water go when it rains, if I can borrow the title from Jeff's talk next week. Well, in this model, you have precipitation, 57, evaporation, 33. These are inches per year. And I apologize for the English units that really are American units, but you do what the customer wants. And this was Whatcom County, and they wanted American English units, whereas I would much prefer to be using the metric system. Yeah, but Canada wasn't getting any. They were not at the table, I guess. So you can see that the precipitation, the 2/3 of it about goes to evaporation, just over 1/3 to stream flow, and then there's small amounts of base flow that are included in stream flow. Well, under historic conditions, there was no irrigation, but you can see that when you look at some of the, say, existing scenario, you can see how evaporation is reduced, stream flow is increased, base flow is increased, as well as the various withdrawals for the various water uses. And then you can examine the full build-out conditions as well. And we were also using this to check that all the numbers sort of added up, and we had closure on our mass balance. So that's at least the calculation error in the model. So this illustrates the changes in flow duration curve. So I looked at, I showed the sort of the aggregate mean annual flows, but that doesn't tell the whole picture. As you change scenarios at various locations, the flow duration curve shifts. So you've got changes in the high flows and changes in the low flows. And sometimes the high flows are higher, but the low flows are lower relative to the historic conditions. And that's of a concern if you're worried about the stream ecology of these streams. This shows the impact on the water balance, and you'll see that there's a thread emerging here. I'm looking quite a lot at the overall water balance, precipitation, and where it goes, and I'll talk more about that later on. But here we've got precipitation being disposed of under existing conditions. That's the cumulative stream flow. That's what Q stands for. The cumulative evaporation, and you can see that where there's more evaporation, there's less stream flow, and where you have artificial drainage, as in the tile drains, you effectively increase the stream flow because the drains were draining into the stream, and you reduce the evaporation because you dry the fields. This illustrates the simulation of a transbasin diversion, the place where the water was taken out of, where the flows were quite high, the place where the water was put back in. So here we've changed this stream quite dramatically because it's now being used as a delivery channel for water to Bellingham City. Naturally, the flow in that river was quite small, but now they're putting a lot in there. This shows the impact on stream flow of future development. So you've got with the sort of full build-out conditions. This is showing where the stream flow has been reduced and where it's increased and so on. So that's all I'm going to show of the model. It's a very brief, maybe not quite brief enough since it's approaching 4 o'clock already, run through what that sort of modeling exercise can give you and the sort of information that you could potentially discuss to see, well, if this management action occurs, that's the consequence, and examine and investigate those sorts of things. I think we need to understand the overall functioning of coupled natural and human system, water systems. So that's, this was a slide that was actually prepared in my work on the Waters Network, but I think it's pertinent here too, in that it really summarizes a lot of what we're trying to do. We've got hydrology, geomorphology, biogeochemistry, engineering, water resources, and human behavior all interacting. And how does this all work? So now for a little bit of a way to think about this that simplifies the world, but it's a useful simplification, and it is a simplification based on where does the water go. If you're thinking about overall water balance, you could have change in storage as precipitation minus stream flow minus evaporation at a large scale, where if you think of water leaving the system as stream flow, let's include the groundwater that leaves a large area as part of that. And if we look at a long enough time, we're going to say, well, the change in storage should average out and be 0. Perhaps we go from the dry water year to dry beginning of the water year to dry beginning of another water year many years in the future. Then you can write precipitation gets disposed of into stream flow and evaporation. So if we put on this axis here, evaporation as a fraction of precipitation, and I'm going to put on this axis here a measure of the available energy to evaporate water scaled by precipitation. And this is following the ideas of Boudico, who wrote about this in this Climate and Life book. Well, there's an upper limit on evaporation. You can't have more water evaporate than is available. So how much water is there gives you a limit on evaporation. So that's the water limited upper bound. Well, we're looking at we're looking at a large regional area. So say the whole Bear River basin. Groundwater is included in the stream flow part. So I mean, you can have certain places where there is mining of groundwater, but without that, there's precipitation gives an upper bound on what can actually evaporate. Or if you're mining groundwater, you can just add that to the precipitation and say that's artificial precipitation. There's also an energy limited upper bound, which is effectively how much energy the sun and wind and the atmospheric system has to carry away water that evaporates. So that's a one-to-one line here because we've got effectively evaporation on this axis and the available energy on this axis. This way of thinking about things provides a way to sort of separate the hydrologic regime into two classes. One that's humid, energy limited, the left-hand side here, and the other part that's water limited, the right-hand side here by this dashed line. All solutions have to basically fit into this blue area because, well, these arrows show the constraints given by water and energy limitation. You can also make the case that if you're in a very arid area where the energy where precipitation is small, so the available energy relative to this precipitation is large, you like to have all the water evaporate. So you're going to asymptotically approach this line. If you're in a really humid area where precipitation is large, so this x-axis quantity is small, you're going to have no limit. Well, the amount of water that evaporates will be based on how much energy is available. So asymptotically, you should approach this 45-degree line. So you might have a solution that goes something like that. So based just on thinking about the water balance, Buriko came up with this idea here and suggested various equations that could represent this curve to characterize how a system might respond. And curiously enough, where I first learned this idea was in lecture number 1 of the class I did from Pete Eagleson, who wrote this book. And that was actually, unfortunately, the only lecture that I ever took from him, because his class, he came in for lecture 1, he gave that lecture, he gave these ideas, and he said, the whole class is you guys doing your own independent readings and discussing it and doing a term project. So it was, he was busy with other things, and that's how that's how the class was taught. So so then on this graph here, you can also get well, if this line gives a solution for evaporation as a function of precipitation, the remnant, the difference, is stream flow as a function of precipitation. So you're getting stream flow and evaporation out of it. So now what might change, what might make that graph go up and down? And one of the things that might make it go up and down is